over to you.
Yes, thanks. So I think that's the first time a lot of you have seen that kind of intro at a conference. So I hope now you know that that's my style. Yes. So now you know I will talk about IoT security with Tsetlin machine. So I also got funded a project for this, and this is the very beginning of that. The whole idea is that we want to create a resource-efficient anomaly detection approach. So I set my students onto this mission, and their question was to how can we train Tsetlin machines to detect anomalies in IoT devices, data streams, and if possible, how does its performance compare to state of the art? That's the mission. But first, let's see the background. So yeah, so IoT was coined in 1999 approximately. And since we have seen extreme growth in this field, we now have doorbells, cars, watches and fridges, basically everything. I see a lot of you guys have IoT devices on you. But clearly this is not without risks. So for example, smartwatch, we have for children, for example, not very good if people can hack this device and take over and monitor your kid's device. Or for example, if you are have a health device that are supposed to tell you something about your health, let's say your heart, for example, and someone goes in and modify the signal so that maybe it tells you, okay, everything is fine, while in reality it's not. So that's one very sad way of attacking IoT devices, just saying that the signal is fine and not at all. So we have seen quite a lot of growth in also these botnets. So basically devices that are compromised and then joins this large network of devices that can attack targets. So one such botnet is the Mirai botnet, which is in most parts composed of IoT devices. So for example, your fridge might be part of this botnet and can target large infrastructures such as, let's say critical infrastructures. And it's quite sad that our fridges can now be part of such, let's say terrorist attacks in the worst case. Yes, so I already said something about the growth. So in 2020, we surpassed 12 billion IoT connections or devices connected, and this is growing exponentially. So we then end up with something like this blob here. These are just imagine they are devices, and they are somehow connected. We also have devices that uses multi-hop technology so that they connect via each other. The network topology becomes quite complex. That's why my nice intro said something about network complexity. So when we get this type of blob, then we have problems because if we want to secure these, oh wow, your computer is about to restart. I disagree. So I snoozed it. I think that is good. Yes. Yes, when you get these types of blobs, it's quite difficult to route all of the traffic, and the amount of traffic that you send from A to B becomes it becomes a lot. So if you want to secure these IoT devices with traditional methods, you typically would send all of the data to some central unit. You would analyze the data and get some results at a incident response team or what we call a security operations center would then analyze and send the incident response team if they found anomalies. So that's not very scalable. Yeah. So yes. So here is an image of what you kind of end up with if you wanted to use the traditional method. You need a data center that takes care of all this traffic. And clearly, this is not very good for the network itself, the global infrastructure, because you now have to send quite a lot of data. Yes. But and this traditional way, there exists some technologies, especially in the deep learning space. For example, Kitsune is one way of doing it within your network. So what you do, you take raw packets, and this is kind of high level as well. You are typically at the TCP level of the packets, but you start with raw packets. You do some pre-processing. Then you can use autoencoders that check if this is a packet that these autoencoders have seen before. So typically how you do it with autoencoders, you send in the data, then you check how large of a difference it is with using mean squared error. So if the error is high, then the network hasn't seen this type of data before, then you can call it an anomaly. That's simply this model. The problem with this model is that it doesn't really work well when you have high throughput applications. So let's say if you have a terabyte per second data flow, you have no chance of putting it into this. You can't even do it for a gigabyte with normal hardware. So again, then if we wanted to do it, then we would have to again try to acquire some H100 cards, just as everyone else is trying to do it for different applications, but there's not enough resources to do it like this. Not scalable. Yes. Yes. So now, and then you have another method, kind of the same as Kitsune, one we called BA IOT, uses autoencoders, and you then use mean squared error to measure how certain or if the network has seen this sample before. If it hasn't, you should get quite a high error, and then you would classify that as an anomaly. Okay, so yeah, now we already figured out that I like visualizations and graphics and sound and epicness. But at least if you think of the line above, that try to visualize how traditional machine learning and deep learning have progressed in this field, and they have a distance left to provide this solution for a scalable way of securing IoT. And then we have our Tsetlin machine, our beloved Tsetlin machine. We have so far, I think, one main paper on this, and there's also some other studies that in a way confirms Darshana's work. And now we try to stretch this a bit further with using technically the same method as Darshana, but we test more hyperparameters, and we test on a range of other data sets. And that's, yes. So, okay, so the end goal, the fridge. So first thing, we know that we already have IoT devices inside this fridge. So I want to take that one out like this. And then I want to put this inside, and this chip that I put now inside, that is a Tsetlin machine enabled. So it should have another chip. I actually forgot it, but imagine that little USB controller, the little black chip, that would be a Tsetlin machine chip instead, maybe. So then we put that inside, and then we have a fridge with Tsetlin machine inside. And if you see it on the high outbound traffic, imagine that we send, let's say, 1 megabit of data from this fridge before it's switching. Yeah, because we have to send all of the traffic, all of the data that this fridge collects, we have to send it to this central unit. But now, since we have a Tsetlin machine inside the fridge, we can just, we don't have to send anything, right? So now maybe it just sends a report when anomalies are detected, for example. That's the main idea. So now we have a fridge with Tsetlin machine inside. Good. So that's the overall idea. So contributions. Okay. So the blue one that exists from before, we did a study, or Darshana did a study, and we extended it with quite a few new data sets we tested on. And okay, so why does that matter? Yes, they have different complexities, different sizes, and so on. So then we can kind of get a broader idea of how well this works. I also I like the idea of sharing. So I always force my students, and after I force them, I prepare it so that everyone else can use it. So this can be used, all of the data sets can be used in the TMU. So you can install TMU, the unified repository, and then you can use the tmu.data package, and then you can access all of these data sets. We also have other data sets, like I've seen quite many of you using MNIST, Fashion MNIST, and so on. All of those are available here. And we also made some methods so that you can load, I think, a lot of data sets from Hugging Face, for example, you can load from this repository. Yes, that's a bit of sidetrack, but anyways. So, so that was the first contribution. The second one is the pre-processing part, which I at least probably someone has done before, but this is different, at least from Darshana's work. So what we did was we just took the raw data stream, and then we Booleanized, or basically just converted it into bits directly. So if you have, for example, a string, then you would one-hot encode it instead. So then, and basically you just append it to a large string of or a large sequence of bits, basically. And this I think is very scalable in the way that now we don't have to train our Booleanizer at all. We just convert to bits, and then we feed it in. So that is a way, in a way, more scalable for these types of real-time applications. Yes, good. Yes, combating the 99.999995 club. That is a problem, especially with these types of these type of problems, because you have 99.99995 percent of data points that are non-anomalies. So typically, if you just use accuracy as a measurement, then you always get high accuracy, right? So you can just do randomly, and it's difficult to get less than this. That's also been one of the challenges when I want to compare my work with others, is that, okay, everyone just use accuracy. So what we did, we balanced the data set as, not the first, but very many don't do the balancing. So what we did, we set a threshold so that we got a decent distributions between all of the different classes in the data sets. So now at least we could prevent getting 99.999. Yes. We also did some importance and correlation between like the target value that we chose. In this case, we used, so for those interested in the tool, we used WandDB for this. It's quite a nice interface. And we also used that for the hyperparameter search, setting up, I cannot remember what was the min and max there, but all of these different parameters we had in our search. Yes. So and the most important one in this case for these data sets was the forget rate of the models. Okay. So now I have some graphs as well. That's nice. So as I said, I tried to not be part of the 99.9 club, but it was difficult to not join it. So we can see here that we got 99.99 on the SICK IDS 27 dataset. We got 99 on .IOT dataset, and we didn't get 99 on the NB15, but we got high accuracy. Okay, so what does that tell me? I will come back to that. Also for these datasets, the KDD99, which is known to be quite simple, it's solved ages ago. We can solve it with any types of machine learning algorithm, almost. And the NSL KDD is kind of updated version of the KDD99, which we got lower, but still quite high. Yes. So what do these results tell me? Okay, that kind of tell me that these datasets, they are too easy. They are just solved, and nobody have really taken a very good effort to try to get some better challenges in this field. All of the research, not all of the research, but a lot of the research, you create a new cybersecurity model, then you test on these data sets, you get 99%, and you publish it in some nice journal. That's kind of the way it's been for the last couple of years, to me at least, when I look at the literature. So here I think we need to think new. We need more difficult tasks to actually test them in, because this works well in the lab, but it does not work well in real life. So all of these results, so as they mentioned in the introduction, I worked at Telenor, quite large telecompany, and none of these models, we cannot use them at all in practice. It's no chance it would not work because of the real-time requirements and the throughput, for example. And also these results we would not be able to replicate this in a real-world scenario. It's just toy experiments that doesn't represent the real world. Yes, so this kind of makes all of the data sets useless, right? So yeah, so what I want to do, I want to create at least a real-time simulator, virtualized, and try to make, not only making attacks, because all of these data sets focus on specifically attacks, for example, DOS attacks and so on. But instead, we could use other type of data like authorization and so on to get a more kind of, you could say, balanced data sets of different types of events, not necessarily attacks. That's not the important part, but instead using different events in the network traffic as a basis for measuring this, because you have quite a lot of events that you could measure on. Yes. Yes, and also we could, the only data set that we didn't get 99.9% on was NSL KDD and NB15. But I also think that if we do some more hyperparameter tuning, we would probably get close to 99 there as well. So, but yes, what is the point? Yeah, so that's the one thing. The data sets are too easy. We need to find a better way to measure. And also, this work was motivated by making this available in embedded systems. So, for example, the ESP32 that you saw, and here we still have some work on making a pure C implementation that works with the TMU framework. So that's some work I already started, but hopefully we will finish that in a few months. Yes, and also we now try this direct way of just converting the data to binary representations, and that worked quite well. But we still need to study if we can do this better and even more resource efficient and time efficient. Yes. So the road ahead, I think, I spoiled everything now. That we need, yes, I spoiled it. So that was the road ahead. Great. So thanks for listening.
Thank you. Floor is now open for questions. Yes.
Hello. Thank you. So you're targeting embedded systems. So I wonder if you looked at model size for the ones that you presented there?
Yes, in the hyperparameters we did check, like we had clauses as one of the hyperparameters, so I guess that is model size. Yes. Right. So, but I rather high. I mean, the models are rather high, I think. This.
Okay. So what do you think about scalability then? If you're targeting ESP32.
Yes. Yes, so yeah, so the end goal is much larger than that, but the first step is to get it to run in just CPU on or like on the ESP chip, not by normal. And we have some work that will hopefully you can reduce the amount of clauses adaptively. So that is kind of the let's say you would set 10 clauses at your starting point. Maybe you then increase it to 20 or 100. And then, or maybe it goes down adaptively to try to always maximize for the lowest, the lowest complexity at the sufficient accuracy, I guess. Yes.
Okay. Thank you.
But yes, but also that is the first step, and the next step is for you experts on all of this to get it in actual cool fancy hardware that I know a clue of, but I can probably get it to work on in C in yes, on the CSP. Yes.
Okay. Any other questions? Yes.
Right. So Well, just to continue, because you are using a one-hot encoding,
Yes.
number of literals is huge.
Yes.
So the model become really huge because of that. So because of number of literals.
Mm.
So as a Booleanization would be appreciated. But my question is also about, just curious, you are using this data set as benchmarks, and at the very end you say, I don't trust them.
Yes.
So what is the reason so that other researchers are using them and then finally now we can't trust them?
Yes, yes, a good question. Why I can't trust them? So that I now I know, because now I've tested. That's right. Before we only had the KDD99 benchmark for Tsetlin machine, and also a lot of people just report the accuracy, and now we also reported the F1 score. It also shows that okay, even then it's high. Then I at least conclude that it's too easy of a problem. And yes, it's when I read the literature, it's like yeah, they come with a new research paper, use KDD 99 and some others, and you get this 99.9 as always. And then then it kind of becomes okay, is this good or bad? Because it's solved, right? So we need new, much larger and balanced data sets at the very least. So did that answer it?
Maybe they already exist.
Yes, maybe. I have not found it. So yes.
There are some data sets with Visa, you know, that the Visa credit card.
Yes.
So it's also large data set. And, well,
yes, good point. So we could probably try some other data sets that are not the same application. So these were specifically network traffic. So that's, but I agree. Maybe we could try other types of data sets. Yes.
Thank you. Any other questions? No, it seems. So I have one final question. So do you have any plan to collect? You were saying that data set is, the absence of data sets. Do you plan to collect data sets, or you can, I don't know, there is a way you can talk to network, providers. They have always these big data sets with,
Yes.
anomaly detection logs and so on.
Yes, I talked with both Telenor and entity security, and it's difficult because of privacy issues. So then they have to put resources to anonymize this. So that is difficult. But what the plan is to create like this virtual environment that's with what we call a chaos monkey. So it's this type of automated engine that tries to kind of drag down services, and the idea is that the whole service that we run, a complex system, should be able to run even if this chaos monkey takes down one service. So this Netflix uses this quite a lot for their robustness testing. So that's the idea, and then you collect all of those logs that are more than just network logs. It would also be access control logs and so on. To get a more diverse, so not necessarily look at network traffic specifically and network related incidents, but also access control and so on. Yeah,
Makes sense. Okay. So no more questions. Thanks to our speaker.
Yes.